So this is Barry's presentation with a few co-authors that he'll introduce as well. How do we get to the?
I think they'll get the slides up top. So yeah, this is going to be tough to follow with what is really just a traditional research presentation on automated cartographic generalization. I will say, I mean, I was a generation younger than Lynn. He was a big presence at conferences. I didn't know him personally so well, but I remember he was widely published in a paper that he wrote on a fuzzy set theory representation of hills. You know, one of the many topics that he looked into was an inspiration for my PhD dissertation. The other thing, and for those who don't know him, why are we talking about him? He was such a tireless supporter of integrating government researchers with academic researchers, and if it weren't for those efforts, the project that I'm going to talk about today would never have happened. So this project is in collaboration with Dr. Barbara Buttonfield at the University of Colorado and Ethan Shavers and Larry Stanislawski at CGIS at the U.S. Geological Survey. And it's adaptive cartographic generalization with scale-specific sinuosity distributions. I should have said adaptive cartographic generalization of hydrographic features of streams and rivers. Normally I would start the presentation telling people what cartographic generalization is, why it's important, and not only for constructing maps, but for providing data sets that empower, you know, people and organizations that don't necessarily have the skills and computer resources that we have as academic researchers, empowering them to create their own maps. But with this crowd, obviously, you guys all know the importance of cartographic generalization. So I'll jump straight to the narrow topic, which is exploring the idea of adaptive feature generalization. So if you have a large database of streams and rivers, you could apply a one-size-fits-all workflow for simplifying, smoothing, otherwise generalizing these features. But you might get better results if maybe you break up the features into, one class of streams that has many small meanders and apply one workflow to that class, and then another class of streams that has a few large meanders. You might need a completely different generalization workflow to get better results. So that's the basic idea. And so our research question is kind of two-pronged. First, can we develop an automated procedure for classifying streams based on multi-scale morphometry? And second of all, if we can develop such a classification, can we then use that to support adaptive cartographic generalization workflows? And this is very preliminary. We have some initial results, but we have a long way to go. This is not a new idea. Dr. Buttonfield expressed this idea very eloquently back in the 1980s. There has been some work on it since then, but there hasn't really been anything that has captured the morphometry of streams at multiple scales and then fed that into cartographic generalization. So that is our hopeful contribution. So I'm going to skip over the outline in the interest of time. You guys will see the progress as we go forward. I first need to define the concept of scale-specific sinuosity. Now, we have presented on scale-specific sinuosity at a couple conferences, and we've also just submitted a manuscript to a journal. So I'm not going to spend time on the technical details of how it's derived. For those of you who are familiar with the Richardson plot, it is a direct extension of the Richardson plot. So what we're doing is we're capturing the degree to which observable detail decreases as the resolution of your measurement instrument decreases. And we are capturing that. What I do want to spend time though is explaining how to interpret the scale-specific sinuosity distributions, which essentially partition sinuosity into different components at different scales and can be interpreted as a histogram or a frequency distribution. So to explain that, we have here 5 obviously artificial features. A, B, C, D, and E, and we have their corresponding S3 distribution graphs on the right. And there's really sort of two patterns here capturing variations in degree and a scale of sinuosity. So going through the first half A, B, and C, we go from a straight line to a line with a few small meanders to a line which is all small meanders. And so on the S3 distribution graphs, A, B, C, going from flat, going up a little bit and going up higher, but all at the same position on the x-axis because the degree of sinuosity is increasing, but the scale, the size of the meanders is not. So they're all in the same position on the x-axis. And then the second half of this, going from C to D to E, the lines themselves go from small meanders to medium-sized meanders to large meanders. So if you measure sinuosity in the traditional way, length over end-to-end straight line distance, they're going to have exactly the same sinuosity value, so the same overall degree of sinuosity. But obviously the size of the meander is changing, so we say that the scale of sinuosity differs, and you should be able to see that on the S3 distribution graph CDE. Same overall height and area of the curves, but you can see the position of the curves moves to the right along the x-axis. So we think this provides a meaningful and intuitive way of capturing morphometry across a range of scales. Now, in order to support adaptive feature generalization, we want to use this, at least in the initial phase, to classify streams based on their morphometry. And to support classification, we need a measure of dissimilarity between features. The problem is that we are capturing we need to capture differences in both the degree of sinuosity and the scale of sinuosity, and ordinary dissimilarity metrics like the Sorensen metric or the Jacquard index don't do that. So we are adopting something called the Earth Movers distance from proposed by Rubner et al. In 1998. There's actually a precursor in the mathematics community. It's sometimes called the Wasserstein metric. But the basic idea is that we're going to treat each distribution as if it was a pile of dirt. And we're going to ask the question, how much effort would be required to move the dirt from one pile into the position of the other pile? So the effort is a function of the mass of the distribution multiplied by the distance it has to be moved. So it's a really clever metric. We need to make a couple adjustments because the original metric as proposed assumed the two distributions being compared have equal total mass, but S3 distributions don't. So we need to allow for removal of mass, but if we do that carelessly, we're going to violate the triangle inequality, so we have to make a small adjustment to make sure we don't do that. But those are details. The basic idea captures what we want in terms of measuring differences between the scale-specific sinuosity distributions. Okay, so now we're going to move on quickly through a preliminary experiment to see if we can use this measure of sinuosity across scales to classify streams and then to perform adaptive cartographic generalization. We're using 50 stream sections extracted from 1 to 24,000 national hydrography data set. These are major, I use the word streams, but these are major rivers. They are all selected from streams that are present on 1 to 10 million scale NHD data, and they're spread across a variety of ecological conditions. So we've got a good representation here. And on this slide, I'm going to move from the bottom up. So again, our generalization objective just for this experiment, we're just going to simplify and smooth the streams with a target display scale of 1 to 500,000. And then we're going to measure how well we did using metrics of positional accuracy, smoothness or angularity, and data volume, which is just the number of vertices. We want to reduce the number of vertices. We're going to support this, we're going to calculate scale-specific sinuosity using stride lengths or scale ranging from 10 meters to 2,500 meters. And we're going to segment every river into sections that range from 10 to 20 kilometers in length. So we're not going to plug the whole, a 200-kilometer river in that varies in its morphometry along its course. We're going to break it up into morphometrically distinct sections. So the segmentation process is we're going to place a bunch of candidate split points along one of these longer streams. Those are marked with upside down red triangles. At each split point, I'm going down on the right-hand side of the slide. At each candidate split point, we're going to look at stream sections to the left and the right at 10 kilometers in length. We're going to compute the scale-specific sinuosity distributions of each section, and then we're going to ask how different are they are. In other words, does the morphometry break at this location? So we're going to use the Earth mover's distance to measure that dissimilarity between the adjacent sections. If we have a high dissimilarity metric, that's a good candidate location for breaking the stream up into sections. And we're going to repeat this process iteratively until all of our sections are less than 20 kilometers. We're not going to break anything up. We're not going to create any sections that are less than 10 kilometers. So the results are constrained to the range of 10 to 20 kilometers in length. We will then perform pretty basic standard classification using the k-means clustering, specifically the Lloyd's algorithm. This slide indicates that we tried k equals 3 to 12 clusters, but what I'm going to show you, what we decided to move forward with is the 5 cluster solution. And the only important variation from the traditional k-means algorithm, which employs Euclidean distance, is that we basically, in a plug-and-play type operation, substituted the Earth mover's distance where Euclidean distance would normally fall in the k-means clustering algorithm. So then we move on. We developed 5 clusters, and then we tried differentially generalizing these 5 clusters. And so what we did is actually what my graduate assistant, Sunita Mahat, did, and I feel bad I didn't get her name up on the slide because she put a lot of work into this. She went through each of the 5 clusters, and then she systematically went through 81 different combinations of generalization parameters using a program that I've developed to perform area preserving segment collapse simplification. We published a paper on that in 2018, but we have a few additional variations that we wanted to experiment with, and also area preserving smoothing, which we haven't published yet, but we have some tools that we're working with and some variations that she employed. So every one of the 5, each of the 5 clusters, she's trying out 81 different workflows for generalization, and the results of each of those workflows, she then went and measured the quality of the results based on 6 metrics, but they're basically capturing the 3 things I talked about before: positional accuracy, angularity or smoothness, and just the number of vertices. So preliminary results, here's an example of the results of segmentation. We think the segmentation process does a pretty good job of capturing natural breaks in the stream morphometry. Sometimes we break things up where there isn't any natural break because we want to get those sections below 20 kilometers for consistency. And here's the results of classification. I find this maybe the most interesting. We do feel that the process in general does distinguish between groups of streams that have different morphometry. We have 5 clusters numbered 0 to 4 because I am a computer programmer. I don't know how to count starting at 1. But we think this does a pretty good job, but it's not perfect, and I have highlighted in orange one stream that I feel personally is misclassified, and you might see some others as well. But I want to call your attention to cluster 4, i.e. the 5th cluster at the bottom, which has the highest frequency of small bends, small meanders, and you can see that captured in the average S3 distribution diagrams on the right. You can see that other clusters have a great deal of sinuosity, a great deal of large meanders, but the S3 distribution of cluster 4 is a little bit to the left of all the other clusters. And that turns out to be significant at our target generalization scale. So here are the optimal parameters that Sunita found for each cluster. I won't go into details about what these are, what they mean, but I will point out that you'll see that cluster 0 and 1 have similar parameters, cluster 2 and 3 have similar parameters, and cluster 4 has the most distinct set of parameters, with that priority metric especially being significant. What we then did is we took the optimal parameters, for example, for cluster 0, and then we applied them to clusters 1, 2, 3, 4 to see what would happen if we used the wrong set of parameters, right? And so we developed a 5x5 matrix, and we measured the percent of a particular target's achieved. We basically chose the worst target metric and what percent of our target did we achieve. But you can see along the diagonal, we achieved almost 100% for 4 out of the 5 clusters. Cluster 2 is problematic. But more significantly, we can see that the generalization parameters that work for cluster 0 also work very well for cluster 1. They work reasonably well for clusters 2 and 3, but they don't work well for cluster 4. So cluster 4 seems to require a different generalization workflow than the other 4 clusters. We're in the process of sort of examining why that's the case. This slide shows 3 different streams, and for each stream on the left we have the original. In the middle, we have the results of a suboptimal cartographic generalization workflow, and on the right, we have the optimal generalization workflow. And it looks like this, and the scale you can see on the bottom right, this is greatly enlarged from what it would appear in print. But we think that the optimal workflow is just getting rid of some of these small bends that would not appear on print. And I'm told I'm almost out of time, but we're on conclusions. We think that the S3 distribution does characterize multi-scale stream morphometry pretty well. The Earth mover's distance seems to do a good job of measuring dissimilarity. Combining the two allows us to perform segmentation and classification. And using those, we do see some benefit for adaptive cartographic generalization. This is still very preliminary. We have just tried a few different methods of generalization. There's many more that we want to try in the future. And I will finish there, and I don't know if we have time for questions, so thank you for your attention.
We should have time for questions.
Thank you. Great presentation. You said optimum results or parameters. So what is the optimum solution, or how do you, is there a reference that you use?
Yeah, no, this is a great question. I should clarify. I mean optimal from the set of parameter combinations that we experimented with. I do not mean optimal in any sort of more, I don't need to show a slide, in any more general sense than that.
So related to this, is there actually a reference data set, so generalized, ungeneralized, that we could use as in the community to evaluate our algorithms?
You know, that's an excellent question. I know there are some efforts to create some such reference data sets. Guillaume Toya at IGN France has been leading some work on that. But we're kind of going in a different direction. Instead of, you know, choosing some reference to try to replicate, we're trying to figure out how we can measure the quality of the output objectively in a quantitative way. And I won't say that the current quantitative measures that we have right now are perfect, but we're also in separate research trying to improve on those quantitative measures. For example, developing a measure of legibility, which is the entire purpose of cartographic generalization. So it's not perfect yet, but that's the direction that we're moving. No.
Anybody else?
Hey, Barry, thanks a lot. On that, one of your earliest slides, you split your scale into 5 categories or classes, right? Can you pull that up?
You mean the?
Yeah. Way back in
This one?
at like your second or third slide.
Oh, the 5 examples.
Yeah. Keep going.
This one?
Keep
Going?
oh no, up.
We're almost at the beginning.
Keep going.
Oh, this one?
No, sorry. Okay, go down. Sorry about that. So maybe go back up one. So how do you determine these 5? How do you determine what parameters are set to decide that A is the straight line, B is these squiggles and a flatness squiggles?
I made those up too.
Okay.
Well, I should say, actually, I responded to a USGS reviewer who told me that my initial diagram was impossible to understand. And so I tried to come up with a better way of just illustrating the two concepts that I want to illustrate, which is differences in degree of sinuosity versus differences in scale of sinuosity. So they're artificially produced to
Okay,
just illustrate.
to illustrate, great, thanks. I thought maybe there was a magical number. Dang it.
Barry, I thought of something else. So this is, so you guys are only focused on morphometry,
Yes.
but there are other like ways of generalizing. Let's say model-based generalization where you use other criteria other than just shape, right? So will this play well with those kind of uses? Because that's what I worked on before, and I'm very interested. Like, how would this help or not help?
I understand what you're saying, but I'm trying to get them into my head an example of like what would be another factor.
Like, you know, if you remember, I worked on groundwater model generalization, right?
Right,
So
right.
they had constraints that groundwater well can't switch this, like the more database kind of constraints, right? And so we just use Douglas Poiker as a distance. What I'm saying is can this be used as one of the criteria and combined with other to do model-based generalization?
Yeah, I mean, the whole process is sort of plug and play, but I guess the question is how would you classify streams based on what would be important for the end result, in
Right.
your case, the groundwater modeling. I'm not sure how to do that,
Okay.
but it's an interesting question.
Okay.
Yeah.
All right. Thank you.